is happening to this? Okay, where are the what is happening to what happened? But now it is. Okay, what is happening to this one? Fine. Okay. So there was this coil, right? And it was in the YZ plane, right? And the magnetic field was in the x-axis. So the current I was flowing, and the aperture or this loop has length L and breadth B. So this was all the information that we had, right? Now we were calculating the force, magnetic force on this current carrying loop, right? So so there are three how many? Four wire lengths, right? So the total magnetic force would be force due to AB and force going from B to C, right? And then force going from C to D, and then D to A. So these are the contribution of all the forces, right? So these are four straight wires combined together and making a rectangular loop. So we have to calculate individually all these forces. And these are vector sums, right? So what do we know about the force? This was force is BIL, right? And we have to find out what is the direction. So this was what do we, right? Is this, so did you guys understand this point?
Yes, sir.
Yeah. So now I was asking to you guys that the direction of this force we can calculate by one is this L cross B method, right? One is this IJK method, or the other one is this Maxwell's right hand thumb. So we have this loop, right? So one, the current is going like this way, then going in this way, then coming back this way, and then going in this way. So this is how it is making a loop, and the magnetic field is in this direction, X direction, right? So this is up down is Y, and then coming out and going into is Z. So this is from here it is coming out, right? From here it is coming out. So we put these direction of all these tips of fingertips. So in the direction of the current and the palm in the direction of the magnetic field, like this way. So when we curl our finger, so this thumb gives the direction of the force, magnetic force, right? So this we understood. So this was, so in here the magnetic force was upwards from A to B. From A to B, so force was upwards. Now can you guys tell me what would be the direction of B to C? So can you guys tell me what would be the direction from B to C? So from B to C is this direction going down, right? So fingertips in the direction of going down, and the curl of the finger. So which direction it is pointing out? Yes, which direction it is pointing out? So we place our fingertips in the direction of current flowing, and this palm in the direction of the magnetic field, and then we curl our finger. So what is the direction that we are getting? Just
Outside.
outside. Absolutely right. So now you guys have understood. Good, good. Outside. So that is k hat, right? Right, guys. Saad, what about you? So this is outside. Good. Now again, what do we do? So let me. So I will switch on to the video, and then now we are going inside. So our fingertips in the inside direction, and the palm in the direction of the magnetic field, right? Then we curl our finger. What is the direction that we are getting?
Down.
Downward. Good, good. Yes, Mariam and Saad, what about you guys?
Yes, sir.
Good. So now you guys have understood. This is the only thing that I wanted you guys to learn. So this is down. Okay. And can you guys tell me about this direction from D to A? From D to A, guys. Saad, what about you? You are not responding. What about you? Yes, from D to A. What is the direction that you guys are getting? Should I again stop sharing? Okay. So now from D to A, we are going in the upward direction. So fingertips in the upward direction. Oh, what is? So in the upward direction, right? And then palm in the direction of magnetic field. Then curl our finger. So what is the direction?
Outwards.
Yes,
Inwards.
Outwards.
inwards, inwards. Right, right. Good, good. So inwards is the direction. Okay, so all the direction that you guys have understood. Good. Saad, is this clear to you? Yes, Saad, Saad boss, are you there? Saad, let us quickly, yes. So let us quickly. Yeah. So did you understand, Saad? Clear? Yeah. And the yes. So okay. And the other way is that to get the direction is that we know that AB, for AB, the length direction is what? K hat, and magnetic field is I hat. So this would be J hat, and this is downwards. So minus J and cross I. So J cross I is minus K and minus so plus K. Right? This is BC. This is AB, and then CD. So CD is going inwards. Inwards meaning minus K and cross I, right? So K cross I is J, so minus J, and similarly we will get what is this? Is upward. Upward is J cross I, so minus K. In this way we can also do this, right? So now let us write all the values. So B is magnetic field magnitude is B, current is I, and length is how much? L, and direction is J hat. Clear, guys? For BC, magnetic field is same, current is same, but this length is B, and direction is what? K hat, and then plus B I, and length is again L, and then direction is minus J, and then again B, I, and this is B, and direction is what? Minus K. So BIL J hat plus BIB K hat minus BIL J hat and minus BIB K hat. So BILJ cancels, BIB cancels. So this is 0. So F net is 0, right? So F net is 0, but we are getting a curl effect. So we are getting a couple, right? So in the case of the dipole, you guys learned that in the presence of electric field, the force was 0, right? But we had a net rotational effect. So do you guys remember? Do you guys remember? So we had this external electric field, right? And a dipole was present. This was dipole moment, and this is q charge minus q charge. This is q charge. So the net force, the net force in this part was in the right and in the left. So net force was 0, but we had a rotational effect, right? And what was the rotational effect? Do you guys recall?
PE sin theta.
Yeah, P sine theta, which was P cross E. Correct, guys?
Yes.
So similarly, that is electric force. So similarly, we will have a magnetic, due to this magnetic moment, we will have a magnetic torque which would be M cross B. So taking the analogy, same analogy from this electric field. In the presence of magnetic field in the loop, we'll have a net uh, torque. Net force would be 0, but there would be a rotational effect. So what would happen is that this loop will experience some torque. So this will rotate. This will rotate in some angle, right? Either in this way or either in this. So this is what we use in the dynamo generator or these kind of things, right? So this is what we call the torque on a current carrying. Is this clear, guys? Oh, Aisha, you want me to tell you about the direction in IJK component again? Okay, good, good. So yeah, good, good. This is what I want. If you guys didn't understand one thing, then you please ask. Okay, so uh, I am saying that what did we calculate it? So magnetic force was I L cross B. This was the magnetic force, right, Aisha? So for the case of this loop, the direction of L current, the direction of current is in which direction?
K.
Your voice is breaking, Aisha.
K direction.
K hat, right? So the direction of current is in K hat direction, and magnetic field is in the x-axis direction. So in the x direction. So this is always I, right? And what do we know? We know that K cross I is J. Understood? So
Yes, sir.
in going from A to B. Similarly, in going from B to C is downwards. So minus J. Understood?
Yes.
And the magnetic field is I direction. So J cross I is what? Minus K, and minus of minus K is what? K hat. Understood?
Yes, sir.
Yeah. Similarly, in going from C to D, so we are going inwards. We are going inwards. Inwards meaning minus k hat, and magnetic field is in I direction. So K cross I is J. So minus J. Similarly, going upward is J direction, J hat, and J cross I. So in the opposite direction, J cross I is minus K. So this is how we can also understand the direction. And you guys already know the Maxwell's thumb, right?
Yes, sir.
Okay, so this was C to D and this was D to. Okay, so this was the torque on a current carrying loop, and this is if M is perpendicular to B, so sine theta is 1, right? So this would be MB, right? And M is how much? How much is magnetic moment, guys? Do you guys recall?
NIA.
Absolutely. Good, good. So it means that you are revising. NIA. So this is the torque. Please remember this. So if this is clear, you guys, please note up to this point. And if you guys have any doubts, please ask. And whenever you guys want me to, yeah, scroll down the screen, you guys, please tell. Yeah, whenever you guys want me to scroll down the screen, you guys, please tell.
Second spot.
So we will see in the next chapter that how these electric field concept that we understood and the magnetic field concept, they are very analogous, right? So we will see that yeah in the next chapter. So whenever you guys have finished noting, please tell.
Done.
Done.
Done, sir.
Saad, what about you?
Done, sir.
Okay, so now let us move on to the last topic, which is moving coil galvanics, right? Okay, so as the name suggests, we have a moving coil. So a coil which is moving, and due to the movement of this coil, we can detect something, right? So what is the use of this moving coil galvanometer? But we'll come to this later. First, we have to understand a few things, right? So first thing that we have to recall is, let's say that you have a spring, right? And you stretch. So you stretch this spring by this mass. So what happens to this string, right? You stretch this string. So this is displaced by some distance x, and then you release this spring. So what will happen to this spring? Yeah. So let's say you have a spring. This is not a spring, but let's say this is a spring. So you stretch this spring in one side, this other side, or maybe both the side. So you stretch this spring and then release it. So what will happen, guys? Let's say that you are stretching this spring in this direction. So what will happen?
The displacement region.
Yeah, so it is displaced by some distance, but if I release it at this point, so what will happen if I release this spring? It will come back to its initial position, right?
Okay.
And why is this happening? Because if I am stretching or if I am pulling this string in the right hand side, so something is acting in the opposite direction, right? You guys already know. So what is that thing? Yes. What is that thing, guys? Hmm. Mariam, Saad, and Aisha, can you guys recall this you learned in your 11th class?
Could you repeat your question?
Yeah. So do I have any spring? I don't have. Yeah. So this is a spring, and I stretch this spring, right? But
Yes, sir.
yeah, but if I release this spring from this point, so it will come back to its original position. Why this is happening? If I am
Um,
stretching,
Hooke's law.
yeah, what did you say?
Hooke's law.
Hooke's law. Yes, absolutely right. Good. So Hooke's law. Because there is some restoring force which is working against this force, which is working against this displacement, right? So it is pulling it in the backward direction in its original state. So as you said, that is Hooke's law, right? So okay, so yeah, so the Hooke's law says that the force is directly proportional to x. So F is minus k, right? This is uh, this is what we know, right? So the displacement is happening in the x direction, right? So there is a linear effect. But you guys have seen the old telephones, right? So the old telephones, what was the structure of that old telephones? It had some dials, right? So not the numbers, but dials. So first we had to rotate that dial, and then it will come back to its original position. So do you guys remember those telephones? Right? So the in the old 80s or right 80s or 90s, something like that. So in that period, we had some rotating telephones, right? So the numbers are rotated, and then it will come back to its original position, and then you dial number 9, something like that. So it will rotate, and then it will come to the original position. So there is some spring, but it is not acting linearly, but it is acting what? How it is acting? Yeah, how is it acted upon? So now the spring is like this, right? It is rotating. So if you are stretching this spring in this direction, so it is creating a rotational effect. So it will come back to in this position, right? So it will create a rotational effect. Okay, is this part clear?
Yes.
Okay, so then now you will not have the linear force, but the angular force. And let's say now the displacement will change to what? Theta, right? So this is how much you have moved. Then it will come back to its original position. So this would be neglecting the minus sign. This would be K. And let's say this is, so in the textbook, it is written like phi angle. So let us take it as phi. So this is the rotational analog. Is this part clear, guys?
Yes,
Is, okay. So the basic structure of this moving coil is exactly like that. So something you have a coil, right? You have a coil which is wrapped in some soft iron core, and it is creating some rotational effect, right? So it is creating some rotational effect. The coil is moving, but due to the Hooke's law, it is getting back to its original position. So then you have some deflection, and in that way you can calculate or you can see that whether there is some current is flowing or not. So this is what we mean by moving coil galvanometer. So what is a moving coil galvanometer? Moving coil galvanometer. So it is a device. It is a device which is used to detect the current. And how does it work? So it works on the principle that a current carrying loop creates creates a torque, right? So the exact thing that we learned in our previous topic, so that is what this moving coil is based upon. So what is the construction of the moving coil galvanometer? Okay, so construction. So you have, right, you have mag two magnets, right, which are providing the, right, so these are two magnets, and in between you have a cylindrical soft iron core, right? And in this cylindrical soft iron core, uh, the wire is wrapped, right? So some wire is wrapped. Okay, and then it has some point. In this point, some spring is attached. So let me, so some spring is attached. Okay, and then it has some, right, arrow. So let me change it color. Right, so it has some arrow which is pointing out, right, and then this is the scale which tells you about, so this is the measuring scale, right, and at the middle you have 0, and then this arrow shows the deflection, right. So these are the two magnets, and they are providing the magnetic field radially, right? So they are providing the magnetic field radially. Okay, so this is the basic diagram of the moving coil galvanometer. But this is a soft iron core, soft iron core, and this is the group. So, right. So, what is this structure? This is a cylindrical structure. Okay. This is a cylindrical structure, and the wire are right. So, wire are joined like this. Okay. And in there you have this. So you have this spring. So this is like okay. So what happens is that, and these are providing some magnetic fields, radial. So these are providing the magnetic. Okay. So and the let's say that if you switch on the current, so if this the current is flowing through this loop, so then later it will have some current, right? So if you have some current in a loop, so they will provide what? If you have a current in a loop, so they will provide what? A magnetic moment, right? So if you have some current carrying loop, so they will provide some magnetic moment, right? And then you have this magnetic field. So this is magnetic field, and then you have this magnetic moment. So it will create what? It will create some torque, which is M cross B. But you can see that these are perpendicular. So this is MB. Okay. So now what you do is that you have this cylindrical, you have this cylindrical soft iron core, and it is wrapped by some current carrying wire. So it has some loop, so it is providing some magnetic moment in that direction, and the magnetic field is passing through this region. So it will rotate this cylinder. So you cannot see the rotation of the cylinder. Okay, so this cylinder is rotating, right? This is rotating, but you see that some spring is attached to it. So if we rotate this, so it will want to go back it to its initial position. So these are providing the rotational effect, right? So in this diagram, in the upper diagram, in here, in the upper diagram, this is the cylinder, right? I have written it horizontally, but the cylinder is going like this. So cylinder is rotating. Cylinder is rotating, so that spring is stretching. So if spring is stretching, then it will turn back to its initial position. So this will deflect, right? So you have this arrow. So you have this arrow, right? In the upper diagram, you have this arrow which will deflect, okay, which will deviate from its initial position. So if it is deviating, which means that we have a net torque, which means that we have a current which is passing through this loop. So in that way, we can detect whether we have the current which is passing or not, right? So the cylinder, if the direction of this current is opposite, so this will move in the other direction. So this will deflect in the other direction, or if the direction is this side, so it will deflect in this direction. This is 0 point, zero deflection, right? So this is the working of moving coil galvanometer. Is this part clear to you guys? Is this part clear? Yes, everyone.
Yes,
Yes,
sir.
sir.
Okay, so this is how the moving coil galvanometer works, right? So this arrow deflected because of the presence of what? This arrow deflected because of the presence of what? Yes, guys. So you guys said that just you guys said that we understood. So what is the meaning of the deflection of the arrow? When it will deflect, guys? Hmm. When it will deflect? Yes, guys. So when you will have a net torque created, and when that net torque will created, because the some current is flowing inside that loop, that is when that this arrow will deflect, right? So yeah, so whenever the some current is flowing inside this loop, then it will deflect, right? So this is the working of a moving coil galvanometer. Okay. Now let me write the what numericals for this. So we have a torque, right, which is equal to what? MV. Okay. And this is creating some rotational effect, which we learned that this is K phi. So this K is some what spring constant or restoring force constant, right? So this is equal to this, as you said, NIA V. So phi and phi would be how much? This would be NIA V by K. So this is the amount of deflection that will happen due to this moving coil galvanometer. So this is the phi angle, right? This is the phi angle. Okay, so can you guys tell that what are the quantities which are constant in this? So in the right hand side, you have all these things. So what are the quantities which are fixed? What are the quantities which are fixed? Yes,
A,
A is fixed, right? A is constant and
B,
B is constant, yes. And
N, and K.
N and K. Good. So these are the things which are constant. Okay, so phi is oh, K. Yes, Mariam. Yeah. So K is also constant. So this is N I O. This is N A B by K, and then I. So this is the deflection angle, right? Angle of deflection. So this will tell us whether the current is flowing or not, right? So you guys please note it down, and if you guys have any doubts, so please ask. This part is just for the understanding purposes, so note it down from there, right? Yeah, and whenever you guys want me to scroll down the screen, you guys So my drawing is bad. You guys please look into the NCRT book and yeah. So draw it here now, but you also consult the NCRT because my drawing is a little bit bad.
Sir, can you please scroll down?
So phi is angle of deflection, right? And n is yeah. I should write all these things. So n is number of turns. A is area of the loop, and what K is restoring force constant or spring constant. Right? P is magnet. Whenever you guys have noted it down, please tell. Whenever you guys have finished noting, please tell.
Done, sir.
Done. Mariam and Saad, what about you guys?
Yes, sir, done.
Saad, so now the next thing is that we know that what is the use of this moving coil galvanometer. So it is used to detect the presence of the current. But can we use it for the measurement of the current? So we are only detecting the presence of current. So in which theory or in which concept when I was doing the third chapter? So in which concept did I use this galvanometer? Can you guys recall? Yeah, in which concept I talked about this galvanometer?
Kirchhoff's law.
Kirchhoff's law. Yeah, right. Absolutely right. So in the Wheatstone bridge, when I was doing this Wheatstone bridge, then in the middle I had the galvanometer. So I said that whenever the deflection in the galvanometer are zero, so that is called the balance condition, right? So to get the balance condition, we use this galvanometer. So that is one use, right? So we can write it as that it is used to detect that this we have already right, but again let us write. It is used to detect the presence of current, right? And the second thing is that it is used to get the balance condition in Wheatstone, right? Now it can also be used as so moving while galvanometer, or let me write it as galvanometer as ammeter, right? So, or we can write, or we should write it as construction of ammeter from galvanometer. So this is the more correct way to say, because the we cannot use galvanometer directly as ammeter, right? So the question is that why galvanometer cannot be directly used as ammeter, right? So I should write it as construction of ammeter with galvanometer, right? So first thing is that why cannot we use it directly as an ammeter, right? What is the harm? So the first thing is that it has a very high sensitivity. Sensitivity. Sensitivity meaning that if we apply a very small amount of current in here, so for a microampere current, the deflection would be a full deflection, right? So we cannot measure the, because let's say you are measuring a 2 microampere current. So it will reach here, let's say 3 microampere here, let's say 4 microampere here, 5 microampere here. So now you have reached the saturation. Up to 5 microampere, it is showing here. And for 10 microampere, it will show here, for 20 microampere here. And generally, in the devices, what kind of current that we get from the devices? In which scale? Yes, in which scale the currents are used in the general devices? So you have 2 ampere, 3 ampere, 5 ampere in amperes, not in microamperes. So the galvanometer will always show this much amount of, right, this much amount of deflection, always. After 10 microampere, it will be here always. So it cannot differentiate between 10 microampere or 50 microampere or so on, right? Is this clear, guys?
Yes, sir.
So that is what we mean by high sensitivity, right? Because after some current, it will reach its maximum point. So this is very sensitive, right? So it will show uh, full deflection. For a small microampere current. This is first criteria. And the second criteria is that it has a very high resistance. So we cannot measure current from it accurately. Why is that so? So if you want to measure the current, how will you connect the device? In parallel or in series? Yeah. So if you are measuring a current, so how will you attach or connect that device to measure the current? In series, right? In series you will connect to measure the current because in series current is same, right?
Yes.
So yeah. So let's say that this is the device that you are measuring the current and you have applied or you have connected a galvanometer, right? Which has some very big resistance G, right? So what it will do is that it will increase the overall resistance because these are applied in series. So this will increase the overall resistance. So the current will decrease, right? The current will decrease. So it will not give the actual current. It will not give the current measurement of current accurately. Is this part clear, guys?
Yes, sir.
Okay. So now then what do we do? What is the resolution, guys? Right. So then what do we do is that to make it an ampere, right? To make, oh, I now know the, okay, so conversion of, the actual word is conversion. So conversion of ammeter from galvanometer. This is the correct. Okay. So now how do we do that? So what do we do is that to resolve this issue, we use a very small resistance called shunt resistance, right? To decrease the overall effect of galvanometer, right? So we use and we connect the shunt resistance, which is shunt resistance, which is RS, in parallel with the galvanometer. So we have a galvanometer which has some high resistance RG, and and we connect a shunt resistance, very small shunt resistance in parallel with it, right? So then this device becomes, so this whole device, then this whole device act as act. Okay. So is this part clear, guys? Is this part? Yeah. So I will do a question, and then it will become very easy to understand. Okay. So I will do a question, and then you guys will understand that what is the use of this shunt resistance. Okay. So first, you guys quickly note it down. Otherwise, again, we will not be able to complete this chapter. So, okay. From here, you guys please note it down. And I will explain it again. Aisha, don't worry about it. I will explain it by an example.
Okay.
Sir,
Yes, Maria.
sir, are you going to take extra classes on Saturday?
Okay, because we are finishing this chapter today, so I guess there would be no need to take the extra class. But if you guys want to take the extra class and have some doubt, clear some doubt, then I will be happy to help. Yeah. So do you guys want to take that extra class? Yes.
No, sir.
Good, good. Then relax, guys. Then you guys prepare, right? So then you guys revise. Okay. Yeah, because I thought that I wouldn't be able to complete this chapter, so that's why I thought about but we have 20 minutes. You guys quickly note it down because I want to do the voltmeter also. So you guys quickly note it down.
Done, sir.
Done. Oh, good. Saad and Aisha, what about you guys?
1 minute, sir.
One. Okay.
Done, sir. Okay. So whenever you guys have noted it down, please tell.
Done, sir.
Done. Good. Uh,
Done, sir.
Saad, noted. Yes, Saad. Okay, good. So now let us understand about the idea of this shunt resistance. So I said that, what did I say? That if we directly use the galvanometer as ammeter, so this is my galvanometer which has some resistance. Let's say this is, who got disconnected? Oh, so Saad got disconnected. So this is my galvanometer. Right. I have not added any shunt resistance, right, guys? And now this is connected to the device whose current I want to measure, right? And let's say this is okay. So this is the whole connection, right? So this is 3 ohm resistance, right? And let me say that this is 3 volts voltage. Okay.
Now, if we have this galvanometer, so it has a very high resistance, which is, let's say, 60 ohm, right? So now you guys know that already, that this is 3 ohm, this is 3 volts. So what should be the current that I should measure? What should be the current? So 3 by 3, I should get 1 ampere, right? This is the ideal. This is the ideal condition. I am connecting a measuring device, right? It should not affect this measurement. This is the idea. Understood? So I should get the ideal. This is called the ideal condition. Okay, I will talk about this, but okay. So I should get 1 ampere current. What does this guy do? This galvanometer do? So now I have a device whose this is 3 ohm, and then this is 60 ohm. So now how much resistance do I have in the circuit? How much resistance? So I have 63 ohm resistance in the circuit. So now what would be the current that I will get? And how much is this? How much is this? So can you guys tell me how much is this? 63 divided by 63. So 0.0476 ampere. So I am measuring the current, which is this. So the current has reduced so much, but this was not the whole purpose. So this guy has affected the measurement, right, guys?
Yes, sir.
So that is why we cannot directly use this galvanometer as a current measuring device. Clear? So this was this part, this question part, right? Now let us see the magic of this shunt resistance. Now, so what do I do is that I have a shunt resistance which is 0.02 ohm. Okay, this is my shunt resistance. So what do I do is that I apply this shunt resistance parallel to this device. So I have this 3 ohm resistance, and I have this galvanometer. So whose right, whose resistance is 60 ohm, and then I have added some shunt resistance which is 0.02. So now what is my, so this is 3 volt, right? And this is my ammeter, not ampere, ammeter. So what is the overall resistance of this device? Ammeter. These are in parallel, right? So one in this ammeter device, so R ammeter, this would be 1 over 0.02 plus 1 over 60. Am I correct, guys? So this is 1 over RA. This is 0.02 into 60, and this is 60 plus 0.02. This is how much? RA would be reciprocal. So 0.02 into 60 divided by 60.02. So how much is this? This is 6 twos are 12, right? So this 10 goes over, so I have 1.2, right? Divided by 60.02. So how much is this?
So
Zero
one
point zero one.
0.60.0. Right. So, okay. 1.2 divided by 60 point.
0.019.
Okay. Good. So 0.0199. Right. So this is the resistance that I have. Now, what is the overall resistance that I have? So this is 3 ohm, and then this is RA, which is 0.0199 ohm, and then I have this 3 volt voltage. So now what would be the current that I will get? I will get 3 divided by 3.019. So how much is this? Plus equal to and then
0.993.
0.993. Good.
Yes, sir.
So now you guys can see the magic. Now I am measuring this current, which is very close to this actual value, true value, right? So before I was getting a very drastic change. This was not the actual current, right? But due to use of this shunt resistance, we have been able to calculate or measure the current accurately. Is this point now? Is this point clear to you, Aisha? Is this point clear
Yes,
to
sir.
you? Good. So please note down this example. Right. This is an NCRT problem. It is already there, but this was the idea of that exam. So please note it down. And then you already know that how do we connect the ammeter. So we connect the ammeter in the series, right? Please quickly note it down and then we'll do the voltmeter also. So I will directly write the voltmeter and then this chapter will be over. And you guys have the class assessment today. So please, yeah, take that test also.
Done, sir.
Done. So again, please do down. So this is use of, this part is use of shunt resistance. Oh, you have 9 minutes only. So quickly note it down. Whenever you guys have not done. Okay, where did Saad go? So this was a crucial point. Okay, now what are the important things about ammeter? So ammeter is
connected in series to measure the current, right? And what do we have? So we have current sensitivity. And what is that? So we know that deflection angle, right? Current sensitivity is the ratio of deflection angle and current, right? So phi was what? This was N, B, and A divided by K and I. So if we take this I in this side, so this is phi by I, and this is NBA by K, right? So if we can change the number of turns, so then the sensitivity will change, right? So this is called the current sensitivity, ratio of deflection angle by current. Okay, guys, understood?
Yes, sir.
Now the next topic is conversion of galvanometer into voltmeter, right? So again, we cannot directly use galvanometer as voltmeter or voltage measuring device because it will affect the measurement of the voltage. So what do? We uh, we connect, right? So this is our galvanometer and it has some resistance. So we connect a very large, right, resistance RL to correctly measure the voltage, right? So we connect a very large resistance to galvanometer to make a good voltmeter, right? So this is how we make a voltmeter, right? And again, voltmeter is voltmeter is connected in series or parallel to the device. How is it? How is voltmeter connected to measure the voltage in a device? Yes,
Parallel.
parallel, right? Because we know that in parallel voltage is same. So voltmeter is connected in parallel to measure the voltage, right? So we have this voltmeter and we want to measure this device voltage, right? So this is how we connect this is how we connect the voltage parallel to this device, right? And then we have, so let me draw it for the ammeter also. So for ammeter, you guys already, this is the device and then this is the ammeter. Okay. And the similar thing which is voltage sensitivity. Sensitivity. So what was the current sensitivity? What was the current sensitivity, guys? Hmm. Just a moment ago we learned. What is current sensitivity?
Ratio of deflection equilibrium.
Yeah, deflection angle divided by ratio of deflection angle and current. So similarly, what would be voltage sensitivity? Deflection angle with?
Voltage.
Absolutely right. Deflection angle with oh. Oh, who got disconnected? Oh, Mariam got disconnected. So deflection angle with voltage. So this phi is what? This is NVA divided by K and I. So we want to calculate voltage sensitivity. So divide it by V. Divide it by V. So then this is called voltage sensitivity, and this would be equal to what is I by V or V by I? R. So this is the voltage sensitivity, right?
Yes.
So this is what we called voltage sensitivity. So Mayam has a job. Hmm. Yes, yes, Mariam. So we just talked about the voltage sensitivity. Okay. So the
Yes,
current,
sir.
yeah, current sensitivity is ratio of deflection angle with current. So voltage sensitivity is ratio of deflection angle with voltage. So this is the difference, right? And they are independent. Current density and voltage density are independent. If current sensitivity changes, so it doesn't mean that voltage sensitivity will change. Okay, so this was the last topic. So where should I? This part, right? This part
Yes.
did you guys
No.
note down? Okay,
Yes,
No.
sir.
okay, so this part you guys have not noted it down, so quickly note it down from. Yeah, whenever you guys want me to scroll down the screen, you guys,
Yes, sir.
yeah.
Yes, sir.
Done. Yeah, whenever you guys have finished, please tell.
Answer.
Done. Good. So now your fourth chapter is also finished, guys. So you guys start revising, right? And yeah, so your school will reopen soon, and we have to be prepared already. So we should not prepare in the last time. We should prepare it already. Okay, so you guys please log into your Learnivio account and find the active test. So please tell me if you have found the active test. Yes, guys.
Yes, please answer.
Okay, so good. And then you guys please take that test and you guys can leave, right? So, but the idea is that you guys please complete that test. So, yeah. Okay.
Yes.
Okay. Allah Hafiz, guys. Allah Hafiz. Allah Hafiz, Aisha. Allah Hafiz, Maya.
Thank you, sir.
Yes. And please complete that test. So, yeah.
Yes, sir.
Allah Hafiz, guys.
Allah Hafiz, sir.
Allah Hafiz. Yes. Bye, guys. Allah Hafiz.